Hello, everyone, and welcome to another Qubits presentation. I want to thank my colleague Alex Condello for giving us an overview of open source tools and the new features that we've added. In this talk, I want to build up on that and tell you a little bit more about a new hybrid solver that we've released called Constraint Quadratic Model Solver. At D-Wave, we are bringing quantum computing to businesses, and we are helping our customers solve real application problems. Solving application problems has a lot of challenges, and what I would like to focus on today is part of those challenges and how we have tried to address solving them in best way possible. My name is Hossein Sadeghi. I'm a part of the professional services team, a team of experts with diverse background who help our customers build hybrid quantum solutions to solve real problems. Currently, there are a lot of quantum applications that run on D-Wave platform in many fields and verticals, such as financial services, life sciences, logistics, workforce optimization, and manufacturing. Portfolio optimization is perhaps one of the most well-studied quantum problems in finance that we see a lot of examples and a lot of customers using it. Most notably, Multiverse has built a portfolio optimization using real data, and they have shown that in a lot of cases, our hybrid platform can outperform select set of classical solvers. In drug discovery, Menten AI is leading the effort to bring quantum computing to de novo protein design. And they've shown that they can use quantum computing and hybrid algorithms to optimize a design and optimize the configurations that ultimately result in better binding properties and drugs that we can use to fight diseases. In logistics and workforce, D-Wave and a lot of customers of D-Wave have built optimization solutions. In particular, we have built employee scheduling for a non-disclosed customer of ours with many employees, and we've used up to 500,000 binary variables to optimize the schedules and meet constraints. In supply optimization, yesterday you saw an example of a vehicle routing problem that we solved for a customer and partner of us, NEC Australia. One interesting application is the one that Volkswagen has come up. They use quantum computing in a manufacturing process of cars. And in particular, they optimize the number of times that you change paint in a fixed sequence of cars, and therefore reduce waste and cost. Despite the successes in building applications, there are still many challenges ahead of us. In particular, you can think of these 5 stages as the core steps taken when you build a real application. And in particular, with quantum, modeling and formulation and translation to quantum instructions is a big challenge. So let's say you start with a business problem and you start thinking about how to turn that into a mathematical formulation. An optimization expert or an AI expert usually does that on a daily basis. Then for a quantum application in particular, you need to take those formulations and translate them to quantum instructions. We often find that at this stage, the number of parameters of the problem or the number of qubits that we use increases very quickly. And so we usually have to take a step back and think about our formulation and reformulate in a way that does not increase the number of qubits or the number of pairwise interactions so much. And so this way, the modeling step and the translation steps are highly entangled, for lack of a better word. And this presents a lot of problems. One of them is that it reduces the number of use cases of quantum computing, and every application you build requires a quantum expert. So now let's dig a little deeper into why this translation step is challenging. So a quantum computer, in particular quantum annealing, works with binary variables, and it has a very specific form, and that's Ising-Hamiltonian, or equivalently, it's QUBO. Real applications, however, they don't necessarily use binary variables, or they don't only use binary variables. They use a combination of binary, integer, and continuous variables. Oftentimes, real applications have constraints. Linear constraints, equality, inequality constraints. Think, for example, a budget constraint or a spending constraint, or quadratic constraints, which I will get to in next slides because it's a little more complicated. And oftentimes, when you work with QUBOs and Ising-Hamiltonian, you have to create very large models just to accommodate constraints and accommodate different types of variables. And lastly, once you've come up with a QUBO that relates to your constraints, then it becomes a question, how do you actually tune these parameters to make sure that constraints are satisfied? Or how do you make sure that constraints are satisfied by introducing different heuristics? So this is 6 items, really big ones, and these are the main challenges that you face when you want to solve optimization problems using QUBO formulation. And fortunately, we have addressed all 6 in our new hybrid solver called Constraint Quadratic Model Solver. And the way I'm going to explain this is, before I explain what the hybrid solver is, I'm going to explain what the model is, because the model is really the first step in removing a lot of these overheads and a lot of these challenges. As it relates to applications, Constraint Quadratic Model allows you to model and formulate your problem without having to worry about how to translate them to quantum instructions. And this significantly reduces the complexity. It expands the number of use cases that you can tackle. And really, anyone with the knowledge in math and optimization can start building applications without having to have extensive knowledge of quantum computing. So what is CQM, or Constraint Quadratic Model? It's actually a programming model for the expression of constraint optimization problems. It's open source, and it's part of Ocean in a DIMOD package. You can actually go and see how it's implemented, look how it works underneath, how it keeps track of everything. It allows expressing objective functions that are at most quadratic, using a combination of different types of variables. So this isn't that different from what we had before. It's a quadratic function. One new thing that it supports is that you can have a combination of different types of variables. But something that is very new is that it allows you to express constraints up to quadratic functions. So you can think of CQM, or Constraint Quadratic Model, as a list of quadratic models, where one is a special and it's the objective that you're trying to minimize, and the rest are constraints that you're trying to satisfy. More specifically, it allows handling of inequality constraints. So you don't have to come up with a scheme to define slack variables for your constraints. It just does that automatically for you. And one other new feature that Alex just explained is symbolic math, which actually helps us a lot in building intuitive models using Constraint Quadratic Model. So this new model also supports the new symbolic math feature. So once you know what Constraint Quadratic Model is, it's easy to define what the solver is. The solver is a proprietary algorithm that runs on classical and quantum resources, and it's available through our cloud services Leap through API calls. It accepts constraint quadratic models as input. It has a built-in support for linear and quadratic constraints and equality and inequality constraints. That seems repetitive, but it is crucial to recognize that these constraints are not converted to QUBO when the solver attempts to solve them. They're kept as they are to ensure that the efficiency is as high as possible. And the same is true for binary and integer variables. So currently, these two types of variables are supported, but the solver does not convert them to binary when it wants to solve the problem. So just a little more details. The constraints that we support are essentially quadratic model. So quadratic model can be linear or quadratic. And all the three senses for constraints are supported: equality, less than equal, greater than equal. We've also introduced a new special type of constraint that is one-hot. This is actually in line with our previous hybrid solver, hybrid DQM solver, but we thought that the previous solver was not easy to use and the interface was not very user-friendly. So we redefined that. We still have the same feature in CQM solver, but we've just made that definition of the discrete variables or discrete constraints much easier. So as a result of everything I mentioned, user creates a much smaller and lighter model and uploads it to our cloud services. And one important feature of the CQM solver is that it does parameter tuning automatically because it is aware of the constraints. So if I want to summarize the three reasons why we went into this direction, and in fact, two reasons, is the ease of use and efficiency. So it's now much easier to define constraints because the model supports defining them rather than what you had to do before, which was to take all your constraints and relax them and come up with different ways of adding different types of constraints as part of the objective. So that's all gone now. It's now much easier. And also use of multiple types of variables. So every time you had an integer variable, you had to convert it to binary. So all of that is now gone. And so the modeling and formulation is now much easier and much more intuitive. But again, as I mentioned, it's important to emphasize that there's less overhead on the user side to not have to convert these constraints to objective, but also on the server side, the solver does not convert them to QUBO, and so it can attempt to solve them much more efficiently without causing memory overhead or use of Slack variables. I put parameter tuning here as a separate thing. It's still ease of use and efficiency, but it's something that in particular our customers has asked us to do for every customer project that we did, and now it's part of a hybrid solver, and it's something that everyone can use. So now let's talk a little more in detail about what these constraints look like. So when I say linear constraint, I mean the general form, where you have a linear function, a sum of coefficients times variables, plus some constant equal, greater equal, or less than equal some right-hand side. So there are exactly n plus 2 parameters. In general, order of n, where n is the number of variables. Every time that you wanted to add this constraint as an objective, what you would have to do is to take the difference of the left-hand side and the right-hand side and square it. When you square an objective, an expression like this, you get a quadratic number of terms, which is basically the pairwise product of every variable to each other. So that's order n squared. So it might be okay for 10 variables or 100 variables or even 1,000 variables, but the moment you get to 100,000 or 1,000,000 variables, that becomes prohibitively expensive. For 1,000,000 variables, you need 500 billion terms to express this constraint as an objective. So that's not something anyone would do or be able to do. And it doesn't matter how quickly you scale your solver to accept larger number of parameters or larger number of variables, at some point this breaks down. And so definitely a better way to handle it is needed. There are other techniques that do not require you to square the function and instead add it directly to the objective, but then it introduces new types of variables and you have to solve an iterative problem, a dual form of your function. For inequality constraints, you also need extra slack variables to define. Slack variables are not a big problem if you have a single constraint. Depending on the precision of the constraint, you may need 8, 16, or 32 bits, or even more, 64. Doesn't seem like a big problem if you have a large number of variables, but if you have a lot of constraints, then they add up very quickly, and it becomes infeasible to have so many extra variables. So similar notes about quadratic constraints. They're actually much more complex. The function q, which is the sum of pairwise interactions and linear terms, must be very familiar to you. This is actually QUBO. But in this new CQM model, we allow having a quadratic function as objective and also as constraint. So you could have something like this quadratic function equals a right-hand side greater or less than a right-hand side. So let's think about what happens if you want to process this quadratic constraint. So if you follow the same instructions as before, take the difference of left-hand side and right-hand side and square it, you actually get quadratic number of terms in the number of pairwise interactions, which is power of 4 of number of variables. And you get high order terms like third order and fourth order, which then you need to convert to quadratic terms. So for this reason, really treating the quadratic constraint as an objective is a no-go. And it's something that oftentimes you try to avoid by making approximations, or in some cases, if you have, for example, less than equal right-hand side, you can just add the quadratic function directly to the objective and hope that the coefficient that you select is enough to satisfy the constraint and not overwhelm the objective function. And again, if you have inequality constraints, you need to define slack variables if an approximate method, like I mentioned, isn't possible. So I know that this was a lot of information. So now let's take some time and go through a few examples. So one example that I would really like to talk about often is knapsack. It's one of the easiest optimization problems that you can think of. It's NP hard. At the same time, there's so much that you can learn from it. Normally, we don't think of knapsack as a good example for quantum optimization, but there's so much there that you can learn, and it's actually part of our training modules. So what is knapsack problem? Knapsack, the idea is that you have items with values and weights, and you want to make sure that the value of the items that you ultimately carry in your container or your knapsack is maximized as much as possible. But you don't want to go over the capacity of the container or the capacity of the knapsack. So it's a simple linear objective, which is the sum of the values times decision binary variables that determines if the item is in the knapsack or not. The same is similarly, the constraint is the sum of the weights times the binary decision variables less than equal some capacity. So what happens if you take this problem and convert it to a QUBO? Well, if you have 100,000 items, a QUBO formulation, putting aside the slack variables, will need around 5 billion pairwise interactions. That's a lot of parameters. And if you think about what the actual problem is asking you, it's simply asking you to add up 100,000 items and tell me what the maximum is, or whether the constraint is satisfied or not. So where does these 5 billion pairwise interactions come from? Well, they come from the squaring of the constraint, because the solver can only understand a unconstrained objective function. So let's say that we can support 5 billion. What happens if the number of items is now 1 million? Then that number is 500 billion. So it grows very quickly. With CQM Solver, you can specify the model natively, very intuitively, and only using 200,000 parameters for 100,000 items. And in fact, 200,000 items is just the number of parameters, the minimum number of parameters that you need to specify the problem, because every item has a unique value and a unique weight. So you can't really do any better than that. In fact, CQM Solver can return a high-quality feasible solution in just 16 seconds for 100,000 items. With Cubo, we've never even tried this because it just takes a very long time. And with 1 million, it's conceivable to think that the runtime will be somewhere around 160 seconds. And again, with Cubo formulation, it's prohibitively large that you can't even try it. Okay, so let's take a look at another example, portfolio optimization. So in portfolio optimization, we are trying to maximize the return of assets. So the idea is that you want to select the best distribution of assets that optimizes the desired objective. Most of the time, this desired objective is return. So you want to know what the return of your assets are. But in modern portfolio theory, you don't just want to optimize return. That's something that you can easily do. But you want to do so under a constraint, under the constraint that the risk associated with the investment is as low as possible. You can also think about dynamically maximizing return and minimizing risk, or some other variations of it, which I will get to in the next slide. A similar problem actually happens in a lot of other places where you want to select a set of items, minimize cost or maximize revenue under controlled risk or confidence level. So for example, you want to recruit patients in hospitals, but you want to make sure that the probability of success is more than 99%. And really, depending on the use case, you may want to formulate the problem slightly differently. So for example, let's go back to the portfolio optimization example. So we have mu, which is a linear function of returns, and we have r, which is a quadratic function of risk. So you may want to maximize risk, maximize returns, while making sure that the risk is under a certain limit, Rm. You may want to morph the two together into a single objective and maximize, for example, returns minus risk. If you maximize returns minus risk, you're maximizing returns and minimizing risk. And then you have to decide what alpha is. And sometimes you want to actually look at the range of alpha and, for example, study efficient frontier in modern portfolio optimization theory. And you may want to do the opposite. You may have a target return in mind, but you want to minimize risk for that selection of assets. At the moment, or before today, with Cubo formulation, what you had to do was to either make approximations or settle with one type of objective that is possible with Cubo formulation, and you didn't have the freedom to explore all three options. And most of the time, what would happen is that you would settle for the middle one, morph into one objective. and you would maximize or minimize a combination of return and risk. Now with CQM Solver, you're actually able to go from one formulation to the other with just 2 lines of code. All you have to do is to define the functions mu and the function r, and then subtract them into one objective, or add one of them as the objective and the other one as a constraint. So it's very easy to do, and you have the freedom to easily change formulation to fit your use case. Okay, another example is vehicle routing problem. So in vehicle routing, the goal is to minimize the cost or the distance traveled by all vehicles. You have a central depot where the vehicles pick up packages, and they go visit different locations and they deliver the supply or packages. You saw an example of a demo that we did for NEC Australia yesterday by David Garvin. So this problem is a classic problem. It's very well known, very well studied. There are many ways to solve this problem exactly or approximately using heuristics. One approach that we took is to actually break the problem of vehicle routing into a partitioning or clustering step and traveling cells person problem. So, for example, let's say we have 50 vehicles and we have 1,000 locations. In the partitioning step, what we want to do, we want to assign locations to vehicles, basically telling us which locations a vehicle visits. In order to do that, we need exactly 50,000 binary variables, one for every combination of locations and vehicles. If a location is visited by one vehicle, it should not be visited by any other vehicle. And each location must be visited exactly once. So this naturally is a discrete constraint, where basically we assign options to each location, and the options are which vehicle. And we only select one of them. So we have exactly 1,000 constraints for every location. On top of that, we also have a constraint for each vehicle. Remember that these locations, when they're visited, there's a package or supply that needs to be delivered to that location. So that package needs to be carried out by the vehicle. The constraint is that the amount of package that are carried out by the vehicle must be less than the capacity of the vehicle, less than or equal. So we also have 50 inequality constraints here. So if I take this problem and formulate it as a binary quadratic model, I have to deal with these 1,050 constraints. I need to add slack variables, square them, add them to the objective, and then I start tuning 1,050 parameters. In the demo, we actually used the DQM solver. It's an old demo, where we dropped thousands of constraints by treating them as a special constraint which is always satisfied, and it doesn't need any parameter tuning. So that reduces the number of constraints to just 50. But you still have to tune these 50 parameters, which is very challenging. With CQM Solver, there is no need for parameter tuning because all those constraints are represented naturally. So first of all, in CQM, we can still add discrete constraints. Make sure that we only search the feasible space where a location is assigned to exactly one vehicle. And we don't need to define any slack variables for the 50 inequality capacity constraints. And we don't need to parameter tune. So we only make a single call to the hybrid solver. And observation is that we get more feasible solutions and higher quality solutions, which is very important. But really the point of this slide is that we've gone from 1,050 parameter tuning to nothing. Okay, so let's look at another example, which is employee scheduling. This is a very simplified version of employee scheduling just to focus on one important aspect of CQM Solver. So employee scheduling can actually be a very complex problem. It can, the number of decision variables that you use can grow very quickly if you want to schedule large number of employees over a long period of time with high precision and into different jobs and roles. So one example that we worked with just under 100 employees, we got to about 500,000 binary variables. And also the constraints can be very complex because we are dealing with employees, and employees have constraints and preferences. And we want to make sure that the employee engine that we build, a scheduling engine that we build, is tuned to be as best as possible for the managers and for the employees. So this was actually work that we did with a technical team and also with feedback from scheduling managers and the employees who were basically using this scheduling app on a daily basis. The constraints can be very complex. So let's take a look at a very simplified version of this problem. Let's suppose that we have a binary variable xi, which tells you if the employee X is off on day I. So this is usually the opposite, but here we have 1 for off and 0 for on. So 1 means the employee is off that day. So for the, and let's say that one constraint is that we want to make sure that the employee takes 2 consecutive days off. So the employee may not necessarily be off on Saturday or Sunday. He or she will be off on a different day, but we want to make sure that the 2 days are consecutive. One way, and actually the most natural way of formulating this constraint, is to take the product of every consecutive days, day 1, 2, 2, 3, 3, 4, 4, 5, and so on, and make sure that at least one of these products is 1. So if one of these products is 1, then the employee is off 2 days and the number of days off is consecutive. In fact, the employee can be off more than 2 days. For example, X2 can be 1, and then the product of X4 and 5 can be 1 as well. In this case, the employee is off 3 days, but one of them at least is consecutive. So this is actually the most natural way to think about this constraint. And when we actually try to solve a similar problem using BQM Solver and DQM Solver, we had to make approximations. We had to actually negotiate with the customer to make sure that we can formulate it in a different way that satisfies the constraints, but compromises in some places. But now with CQM Solver, we don't have to do that. We don't have to define any ancillary variables. We don't need to make any approximations, and we can be basically very close to the actual requirement of the customer. So the important takeaways from this talk is that the CQM Solver is easier and more convenient to use. Thanks to the symbolic math feature, actually training and creating examples and exploration has become much more easier. But the fact that you can also define different types of variables and different types of constraints has made this, this model very easy to use. However, it's important to recognize that this isn't just about ease of use and convenience, it's also about efficiency. So the constraints are not turned to a quadratic model right away. An algorithm intelligently decide whether they should be converted or not, and only when necessary. This way, you can actually scale up to much larger problems without having to scale the solver. So we don't support much more variables than before, and we don't support much more biases than before, but the scale of applications and problems that you can tackle has increased significantly because the overheads and obstacles are removed. And one important obstacle that has been removed is parameter tuning. A lot of times we actually are happy with the end result that is QUBO, but the moment we want to do parameter tuning, we realize that it's difficult. It also removes the need for you to decide how many slack variables you need. And modeling quadratic constraints has almost never been an option, and now it's an option that you can easily use and explore and come up with ways to introduce quadratic constraints when your problem demands for it. So as a result of all of this, the use cases of hybrid quantum has now expanded significantly, and the number of people who can create applications using hybrid algorithm has extended to any math and optimization expert. And with that, I would like to thank you for your attention, and I will ask my colleague Alex Candello to come to stage for questions.
Go.
Hey, Alex.
Thanks. All right, well, I get set up so I can get some of the questions that have come in on the chat.
Sounds good.
Can you tell me a little bit about what led to the development of the CQM solver, like what prompted it?
Yeah, sure. So really the reason we went to this direction and introduced CQM solver is because of the feedback we got from our users and from our customers. And when we were working with customers, we realized that a lot of times they are facing similar issues. They have different types of constraints, they have large constraints, they have different types of variables, and really because of that, we started thinking about, okay, what is the best way to tackle these issues, and what can we do to make sure that every customer, every user can define constraints and use best practices consistently.
And could you maybe highlight just really quickly some of what you would use this solver for, and what you would use the BQM solver for, and what you would use the DQM solver for, for users who are seeing all three and not sure where to take their application?
Sure. So, as the name suggests, every time you have an optimization problem where you have to express constraints, it's much better to work with CQM solver. In fact, for a lot of problems, you can start with CQM, and even if you want to explore, for example, if it's still better to convert constraints to objective, your starting point can still be CQM. So I would say that every time your problem has constraints, just use CQM solver, and if it doesn't, explore.
A question from the chat. Is there any chance that a CQM or hybrid solver would produce a worse solution than just the QPU or a CPU solver by itself? And if so, when?
Can you repeat the question?
Sure. Is there any chance that a hybrid solver would produce a worse solution than just the QPU solver, say, by itself, or a classical solver by itself?
Yeah, definitely, it's possible.
Is there a way to find the % of time that a hybrid solver used quantum resources for the overall runtime?
Yeah, sure. So when you submit a problem to the hybrid solver, you get a sample set back. This sample set has a lot of information about what solution has been found, what the energy of each is, whether they are satisfied or not. And one of the information in the sample set is runtime and the QPU access time, and the number of occurrences of each sample. Yeah, you get a lot of information, including timing.
And can you tell us a little bit about where you can find like code snippets or examples or anything to demonstrate use of the CQM solver?
Yeah, sure. So on our Leap dashboard, you can find a lot of resources for how to use CQM solver, how to build a CQM model. There are training materials, there are examples on our GitHub. Most of it is open source, and you can go through all of them and explore different examples.
Sorry, just trying to find a new example. Are there any higher order interactions allowed currently with the CQM solver?
So for higher order terms, it's not something that CQM supports naturally. You can continue to use CQM solver for higher order terms, just like before you were doing with BQM solver, that is to take higher order terms and convert them to quadratic by defining new ancillary variables.
Are there any problems that you think we can now solve with the CQM solver that were just really not feasible before when we were using our other hybrid solvers?
Yeah, sure. So, I mean, take the simple example, knapsack, that I mentioned in my talk. Really, when you go to 500,000 items, it becomes really impossible to formulate that as a BQM. Or either you have to have lots of pairwise terms, or you have to do multiple calls to the hybrid solver. With the CQM solver, that is now possible to do much more efficiently. It's not like real applications or knapsack, but a lot of times you get problems that are combination of knapsacks with something else happening on the side. And being able to express linear constraints so efficiently really helps those applications that were really impossible before with BQM solver.
Are there any problems in the constrained quadratic model space, like in the space of problems that it does solve, that you would consider not a good use case for the solver?
Sure. I mean, there are certain features that are still not part of the CQM solver. For example, surrogate functions and multi-objective optimization. In multi-objective case, you can use tricks, but to formulate it as a single objective. But it's not like multiple objective are supported. Still, if you have constraints that are higher order, they're not supported. So these are still not good use cases for CQM.
Does the CQM solver return multiple answers or just one from the chat?
It returns multiple samples, yeah.
Great. I think one more question then. So you touched on this a little bit, but could you just one more time tell us a little bit, how do you get started? Like what would be the first place you would direct people to go to get started with the CQM solver?
Yeah, sure. So definitely I would start with Leap dashboard, where you can find a lot of resources. From there, you can start by, what is CQM and what is the CQM solver, and then from there, find your way into examples. There are a lot of examples on GitHub that tells you how to go from an application, from an idea, all the way to parsing solutions. You often get an explanation of how the objective function is formulated, how the constraints are defined. You get a lot of good practices in the README files of these examples. Yeah.
And there actually is one more in the chat. Thank you for your questions, everyone. Keep them coming. How can we compare the solution from the CQM to, they say a normal algorithm, but I'm going to say other solvers or maybe to the QPU by itself? Or how do you make that comparison?
Sure. So it really depends on the metric that you have in mind. For a lot of real applications, this is not general, but a lot of them that we see, really getting high quality solutions in short amount of time is really the most important thing. So I would compare the hybrid solver with everything else by just looking at how quickly you can get to high quality feasible solutions.
Great. I think that's all the questions we have. Thanks, everyone. Thanks, Hussein.
Thanks, Alex.